we're going to be looking at is a summary of what you did in term 1, and we're going to be looking at what's called the viewing frustum. Okay, the first couple of weeks, the topic we're going to be looking at is called clipping. It's the next stage in the graphics pipeline, and that starts with something called the viewing frustum. Right, so this is the summary of what you did in term 1, and we're going to be looking at what's called the viewing. I'm going to turn that off straight away. Couple of weeks. Don't know what happened there.
No, it's still live because you had it up in the background watching it live.
Did I have it on? Is it still live?
Yeah, it's live.
Where's live in the corner? I'm going to take your word for it. Okay. That, you know, when you listen to your own voice back, it's horrible. I do not sound like that, hopefully. Anyway, right, this is the graphics rendering pipeline. You may have seen something like this before. These are the steps which we go through in order to go from the very primitive objects, which you saw in a couple of your assignments last term. So you had your cubes, your pyramids, etc. So those are your objects. And there's a series of processes which we go through in order to get from your primitive objects right the way up to what you see on the screen. Okay, we're about halfway at this point. So in term 1, you looked at object space, you looked at the transformations, alignment to get to the screen space. So we're about halfway. In term 2, we're going to be looking at getting the other half and some other things as well. Okay, that's the graphics rendering pipeline. This is sort of thing which it's like a flow diagram which summarizes all the steps which we need to get when you have something like a computer game which is being shown on the screen. Okay, so now I'm going to start the whole, imagine you're in week 1 of last term, and I'm going to go through quite a few of sort of revision recap just to refresh your memory. You've probably abused yourself over the last 3 weeks with too much alcohol, so you've probably forgotten a lot of things. So that's the sort of where I'm coming from. I'm assuming you've forgotten a lot, so apologies if I'm being a bit patronizing here. Okay, so the first thing I'm going to start with is the idea of coordinate transformations. Now, we use 3 main coordinate transformations in graphics: scaling, rotating, and translating. So scaling simply changes the distance of a point to the origin. So if you have a point somewhere and you want to scale it, it just means moving it closer or further away from the origin. Okay. Rotating, so we have in 3D space, we have an X, Y, and a Z axis, and we can rotate about each of those axes by a certain angle. Okay, so if you've got a point somewhere in space, you rotate it about one of those axes by a given angle. Okay. And the last one is translating. So you've got a point in space, you want to move it to another point along a vector, and that's called translating. So those are the 3 main ones we have. You've also got reflection, but I'm not going to really bother about that, seeing it's not massively used in computer graphics. So those are the 3 we have. Computer graphics uses homogeneous coordinates. So instead of a 3-tuple, which you'd normally expect a 3-dimensional point or the coordinates of a point in 3D space to be defined by, we use a 4-tuple. Okay, 4-tuple, you have your X, your Y, your Z, and you've got your 4th element, which I've labeled W here. That 4th element is what we tend to refer to as something like a scaling factor. The actual X, Y, and Z spatial coordinates are found by dividing your first 3 elements by W. Okay, so if you have some coordinates here and you have your scaling factor W, the actual spatial coordinates are X over W, Y over W, and Z over W. For most applications, you can simply set W to be 1. Okay, so you have X, Y, Z, and then 1 afterwards, because if you divide throughout by 1, you're not changing it. A couple of times, for example, when we look at projection, that W is not 1, and it matters, but for all intents and purposes, for most times, it can be 1. Now, why do we have this 4th value? Why don't we just use X, Y, and Z for our coordinates. Well, for scaling and rotation, that's fine. But when it comes to translating, what we want to do is express each of those coordinate transformations in a matrix. Okay. Translating can only be done if we have that fourth element there. Okay. So the reason why we use homogeneous coordinates is because so we can write translation as a matrix equation. Okay, so we saw all this last term. If you want to apply scaling to homogeneous coordinates, you simply multiply by the scaling matrix, which is diagonal matrix with your scaling factors on the main diagonal. Okay, so if you have your coordinates as a column vector, right, so you pre-multiply by your scalar matrix, and that will have the effect of scaling those coordinates. The other convention is to represent your coordinates as a row vector, but then you just swap. You'd have the 4x4 matrix being the other side of your vector. So it's the same thing, doesn't really matter, but it's just whatever convention you use. I'm going to keep with how Killian was doing it by using column vectors as the convention. Although it doesn't really matter which way around. Sometimes you'll have to transpose a matrix if that's the case. Rotation matrices. Okay, so we have three axes, X, Y, and Z. So we rotate using three rotation matrices depending on which axis you want to rotate by. Theta is an angle. That's whatever angle you want. These all assume anti-clockwise direction. If you want clockwise direction, you just change the sign of the sine ratio. Not a lot can be said about that. You've seen them quite often. Really useful, especially when we come to aligning the world space. And translating, that's moving something. Okay, so if you have your points and you want to translate them all by the vector p, okay, you use a translation matrix. Okay, so this is a 4x4 matrix, which is why our homogeneous coordinates need to be 4x4. Not a lot can be said about that. If you had the coordinates as a row matrix instead of a column, okay, so we'd have some row here, the px, py, pz would be on the bottom, i.e. you have the transpose of this matrix. But as I mentioned, I'm always assuming we have our coordinates as a column. And if we do that matrix multiplication, you can see quite simply, you just add in px, py, pz to the corresponding x, y, z coordinates. So those are the three transformations which we apply to our coordinates. Using combinations of those, we can combine them. Now, this is where sort of matrices become really powerful. That computer chip in your games console or in your phone or in your computer, which deals with graphics, is very, very good at matrix multiplication. It's crap at anything else. It's just very good at matrix multiplication. And the reason being is most of computer graphics is simply multiplying matrices together. Okay, so if you have your various transformations, they're all 4x4 matrices. So we can multiply them, doesn't matter what order. Okay, so if you want to apply translation, then rotation, you can do so. In the end, you're going to end up with a 4x4 matrix. Your vertices are going to be a 4 by however many points you have. So those can be multiplied together. So it all comes down to matrix multiplication. So for example, if we wanted to scale, rotate around the x axis, then rotate around the y, then rotate around the z, then translate, we can multiply them in this order to give me a single alignment transformation matrix A. That is then multiplied by your coordinates to apply all of those combined transformations together. Just note that the order of the matrix multiplication is the reverse of the order in which you're applying things. Okay, so the first thing we want to do is scaling. So that's the last thing we multiply. Okay, and the last thing we want to do is translate. That's the first thing we have. Okay, so that's the transformations we're going to use. Back in the viewing pipeline, the first box we had was the object space. Everything in a virtual world is made up of objects. So the whole virtual world is made of objects. You have barrels, buildings, lampposts, cars, vehicles, etc. Each of these objects is defined in its own space, and that's called the object space. So if you've got hundreds of different objects, you'll have hundreds of different object spaces. I use a subscript O to denote object coordinates just to avoid confusion. You don't have to use that. So each object is defined in its own object space, and usually what we do is we center the object about the origin. So that means it's easy to scale and rotate. So if you scale about the origin, you just enlarge in the object or shrink in the object. And if you rotate, you're just rotating it about its own axes. Okay, so when you define your objects, that's what we aim to do. We aim to have them so they're centered at the origin. Usually the base of the object is centered at the origin. Okay, so that's the object space. Objects are made of several polygons. Okay, so going back to sort of almost apologetically to primary school mathematics, I'm going to explain what a shape is. Okay, a polygon is simply a flat two-dimensional area bounded by a closed curve consisting of straight line segments, squares, triangles, hexagons, things like that, trapeziums, etc. The official definition is the corners of polygons are called vertices, and edges, the straight lines, are called edges that join the polygons. Polygons can be characterized. Now, there are numerous. If you do a sort of Google search on characterization of polygons, you'll come up with numerous different types. The main ones we're interested in computer graphics is convex polygons. That's what we want. Convex polygons are well behaved. Okay, they're easy to work with. A definition of a convex polygon is if we draw any line which cuts through our polygon, if it only intersects the edges of the polygon twice, it's convex. If it intersects more than twice, it's non-convex. We want convex polygons. They're well behaved. They work well with clipping, which we'll be looking at over the next couple of weeks. They work well with lighting. They're just a lot easier to work with. So convex is what we want. Non-convex is any polygon which isn't convex. A simple polygon is where none of the edges intersect with another edge. So in other words, they're not sort of twisted around or something like that. And a concave is non-convex and simple. Okay. Traditionally or typically in computer graphics, we want to work with convex polygons. Usually we actually work with triangles. Now a triangle is always convex. It's only got three sides. So any way you cut through a triangle, you're only going to intersect the sides twice. In these notes and in this course, I tend to use quadrilateral polygons because they're easier to sort of define when it comes to filling, coloring in a polygon, they're easier. But in practice, we actually use triangles all the time. Okay, so that's polygons. There's a polygon. Not really much I can say about that. Vertices of the polygons, I tend to use V's to denote vertices, obvious reason. Right, normal vector. You've dealt with this in term 1. Some of the stuff we're doing in term 2 requires a normal vector to be uniquely defined for a given polygon. Now, normal vector is any vector that points perpendicularly away from a plane. So let's say this table has a flat plane on it. This is a flat plane. A normal vector to this table can point straight up, and it can also point straight down. Any vector which points perpendicularly away or makes a 90-degree angle with that table is a normal vector. They're quite easy to calculate. They're just a cross product of any two vectors on a plane. So if we have our polygon defined by vertices v1, v2, v3, etc., we can make a vector on the plane by simply subtracting 2 of the vertices. And sort of standard convention to do this is to subtract two sequential vertices. So this first vector here is a vector going from the first vertex to the second vertex, and the second vector is a vector going from the second to the third. That's just convention. If everyone uses the same convention, it's a lot easier. But the problem is we have here is, since the null vectors can point in two different directions, i.e. they're opposite from each other, sometimes we want them to be uniquely defined. Okay, so when it comes to, for example, lighting of a surface is determined by the normal vector. Now, we can't have that being ambiguous. So what we tend to do is we list the vertices in an anti-clockwise order when we look at the normal, when we look down the normal vector. Now, I'll explain what I mean by that. Okay, so here we have two polygons. Essentially, they're the same polygon. And the one on the left, I've listed the vertices in anti-clockwise order. So let's say I'm looking at this polygon from on top. So I'm looking down the normal vector. As I look at it, I've listed numbered the vertices in an anti-clockwise direction. If I then use this equation here to calculate the normal vector will point towards me, point straight up. If I was to label them in a clockwise direction and use the same equation, the normal vector will point in the opposite direction. Okay, so it's convention to list the vertices in the anti-clockwise order. That always assumes that your normal vector then points towards the viewer. And that's important when we start dealing with lighting. Okay, so that's objects are defined by polygons. Polygons are defined by vertices. Now, how do we define the objects? This is more of a sort of a practical problem. So it's all very well having these sort of mathematically described, but when we're dealing with computer graphics, we're going to have to code them in, we're going to have to program them. So how do we do that? In practice, what we have is we have two arrays or two matrices. One of those matrices contains the coordinates of your vertices. So here's my vertex coordinates array. I call them verts. Don't know why, I probably read it in a textbook somewhere. And each column on my verts array is a separate coordinate. Okay, so you can have n of them. Usually you have millions. In a computer game or something, you'll have millions of these coordinates. Okay, so that's your vertex array. Now, several polygons may share the same vertex, right? And you don't want to have to repeat in your verts array. You don't want to have repeated coordinates. So what we then do is we have a list that links each polygon to its vertices in the vertex array. So, for example, if this is my linked list, which I've called poly, the first row says, okay, this has got 4 vertices in this polygon, and it's using the 4th vertex in this array, and the 3rd, and the 2nd, and the 1st, in that order. Okay, so this is my verts array. This could be 4 by thousands. This is my polygon array. Okay, each row of the poly is a single polygon, and each going across gives me my vertices for the polygon. Okay, so so an object in the computer program is defined by the verts and the poly array. It's quite difficult to really visualize this. Okay, I've made an attempt here. First thing I did when I drew this is I drew this sort of cube here, and I said, oh well, it's the front face of this and the back face of this. But then I thought, hang on, I'm assuming that this front square here is facing us, but if you look at it the other way, it could be this back square could be sort of the one facing us. Depends which way around you look at it. It's like a what they called optical illusion. That's it. Okay, so then what I did is, remembering back to stuff I used to do at primary school. Do you ever used to do this? You used to make cubes and stuff out of flat paper. So what I've done is I've sort of unfolded this cube. So for example, the base of the cube at the bottom is defined by these vertices here. Okay, so this is the base, this is the front, right side, etc. So you notice the front polygon shares a vertex V1 with the left and the base. There's no point in multiply defining V1 in our vertex array. So we define it once, and then we say, okay, the base is defined by vertices 4, 3, 2, 1. The front is defined by vertices 1, 2, 6, 5, and the left is 4, 1, 5, 8, etc. So notice I'm going anti-clockwise, so the normals will be pointing outwards. Okay, so I've got 6. If I have a cube, I have 6 polygons which define the cube. And so the base is 4, 3, 2, 1. The front is 1, 2. Oh dear, front should be 1, 2, 6, 5. Sorry, there's a bit of a mistake there. But that's how we define it. So we have 2 arrays, the vertex array and the poly array. Okay, and that's the object space. So this is similar to what you did in your assignments last term. Okay, I've made a house object. The only difference between this and what you did is I've also calculated the normal vectors and put them onto my object space. Okay, hopefully if it loaded up, should have a MATLAB code here. This is kind of your village code. Hopefully it works. There we go. Oh dear. I've made it generate loads of different spaces. If I get back to my first one. Okay, so there you go. There's, for example, there's my house space there, and I can sort of drag it around, and you can see the normal vectors are all sort of pointing away from the center of the object. You don't always want that, but most cases you do for when it comes to things like hidden surface removal and lighting. So you usually want your normal vectors pointing away from the center of your object. Back to the slides. Okay, so you have your object defined, you translate, scale, rotate, etc. You build the world space. Now, this world space is your actual 3D virtual world. This is your computer game. This is your sort of virtual reality thing. Okay, so here I've got a very, very simple world space, got for sort of presentation reasons. One thing to notice is we have the Z as our horizontal coordinate and not the Y. Usually with the right-hand system, you have X, Y, and Z point straight up. But for computer graphics, when we display it on a screen, we have our X and Y going straight up. So our Z is our horizontal coordinate. So this is my world space. What I've got here is P. This is where you are. This is where the viewer is. Think of the P as like a camera position. And we're looking at the world space to C, which is our center of view position. Okay, so therefore we're looking along this D vector here. And what we want to do is we want to move and align the world space so that we're looking along that direction of view vector. And you saw how to do this last term with one of your assignments. You first translate P so it's at the origin, then you rotate around the Y axis, then you rotate around the Z axis. And in doing so, okay, I'm just going to sort of, this is probably all old hat to you. We create an alignment transformation matrix, do all of that. Oh, wrong way. To do so, what then happens is the origin is where our viewing position is. And we're looking at the world space along the Z axis. Okay, so this is sort of like, I tried to draw an eye here. This is sort of which direction we're looking at it. So this is my aligned world space. To get that onto the screen, we sort of project onto our viewing plane. So what we do is we add a plane which is parallel to the X and Y plane, some distance along the Z axis. And what we want is we want to create a 2D representation of that, what the viewer should see of the 3D space. So that's the next step. So that's your screen space. And this is done using perspective projection. Okay, so imagine this is your world space. Okay, this is the Z axis. And going up here is the Y or X axis, doesn't matter which. Okay, and this is a point here in the world space. Now, if our viewing plane is at a distance n away from the origin, the position of that point P on the viewing plane should be at PS, PS for screen. And that's found by creating a projector line from the origin to our point P, and where the projector line crosses the viewing plane, we have our point PS. That is perspective projection. Now we can use that to create a coordinate transformation. Quite simple. Okay, if you look at the triangle OAPS, this little triangle here, it's similar to OBP. Similar means it's just the same triangle, just scaled up or down. So therefore, the ratio of x, this is x, this is the length x, over z. So x is p minus b, z is b minus o. That ratio is going to be the same as the ratio of PS to A and A to O. So we have this equality here. And we can, therefore, this gives us our screen space coordinate for x is simply x over z times f. Now that f should be an n, sorry about that. Okay, and we do the same for the y coordinate, and we create this perspective projection matrix. Quite simple. Okay, so this gives us our perspective projection, but what we have here is the scaling factor is z over n. So if we divide x, y, and z by z over n, we get our screen space coordinates. Okay, so that's perspective projection, and that's what it looks like. Okay, so if we take the screen space, the world space, sorry, project it onto the screen space, that's what you get. I think I could show you that a little bit better. Here we go. Okay. So if I sort of twist this around, so I'm looking at it where the viewer should see, you can see the house which is closest to the viewer is bigger, and the house furthest away is smaller. You can actually sort of look at it from on top. You can see that the perspective projection is actually sort of skewed things slightly. Okay, it's not. These aren't parallel lines anymore. Okay, you can sort of see it sort of skewed around. Okay, so that's where we're up to about assignment 6 in our sort of viewing pipeline. For the next couple of weeks, we're going to be looking at clipping. Now, clipping's all about removing stuff that the viewer can't see. Okay, what's written on that wall behind you without turning around? Can anybody tell me what's written on that wall behind you? Why not? Can't see it. Why can't you see it? Yeah. Okay, you've got binocular vision. Binocular vision, you can only see in front. You can look what's written on the wall behind you now. There's nothing there. Sorry. I just didn't want you turning around. Okay, so essentially that's what we're doing with clipping. Anything we can't see gets removed from here on in. Okay. Problem is, some things are partly in our vision than others. Okay. Some things will be half inside and half outside the viewable region. So that's what we're going to be looking at, clipping. We're going to be looking at 3 methods over the next sort of week or so. Right. Okay, in order to sort of set that up, we're going to introduce the idea of the viewing frustum. Now, as I just mentioned, you can't see things which are behind you. In fact, I mean, if you know about your peripheral vision, how far is it before you can actually see something if it comes sort of round from the side? I don't know. About there for me. Okay, so your viewing frustum is everything which is sort of in front of you in your peripheral vision. when you're viewing a virtual world through a screen, the visible region, okay, this is a screen here, okay, and that's the viewer. The visible region is defined by this sort of, I don't know, sort of squarey, coney shaped thing. It's probably got a posh name, but I don't know what it is. This is what we call the viewing frustum. Okay, so this is your screen. Anything outside of this viewing frustum is ignored. Okay. And this viewing frustum is defined by your bottom left, top right coordinates of your screen. So that's the screen you have. Anything in this like coney, squarey shape here is included in our virtual world from here on in. How do we define the viewing frustum? It's defined by three things. One is how far your viewing plane is from the viewer. That's that n value. Okay. We've also got a far viewing plane. You can't see forever. Okay, you can't see forever. There comes a time when something which is so far away you can't actually see it. In computer graphics, we have a far viewing plane to save us effort. There's no point rendering things which are really, really small on the screen. Our hardware is not powerful enough. On sort of older generation games consoles, you had what you call fogging. So when you look at you look at virtual world, things in the distance sort of look foggy. That was introduced so that the computer would have less to do, less work. Okay, so the viewing frustum is defined by the near viewing plane, which is distance n from the viewer, and the far viewing plane, which is distance f. Okay. The width of the screen is given by the field of view angle. That's how sort of wide your vision is. Okay, so the larger the field of view angle, okay, the wider your sort of vision. So a small field of view angle would sort of reduce L and R, say, to here and here. Okay, so if you're given a field of view angle, which is how it's defined, L is simply minus n times tan, half field of view. And your R is simply minus whatever L is. Okay, so what you can see in the visible region is defined by field of view angle. You know, if you ever play a game where you need to zoom in on something, all you do, easy way to zoom in, is you just reduce the field of view angle and has the effect on zooming in. So, I don't know, lots of shooting type games have got weapons where you zoom in, and that's all it's doing, is reducing the field of view. Okay, aspect ratio. So the other thing which defines the viewing frustum is the aspect ratio. What's the width to height ratio of your screen? So width to height would be your R coordinate minus your L divided by the top coordinate minus the bottom. Okay, so if you have an aspect ratio, which is what we normally have, 4:3, 16:9, etc., you can calculate, well, we assume that the bottom coordinate is simply minus the top. Okay, so we want the center of the screen to be the origin. So the top coordinate is simply minus whatever the bottom coordinate is. So if that's the case, so if we insert B is simply minus T, and rearrange, and therefore the top coordinate is R minus L over 2 times the aspect ratio. And once you've got the top coordinate, minus it, and that gives you the bottom coordinate. So we can calculate L and R using the field of view angle. Then we calculate T and B using the aspect ratio. And that gives you your screen. Once you've got your screen, you can calculate your viewing frustum. Okay, we want to make life easy for ourselves. We're mathematicians. One of the main things we always do is we want to make life easy for ourselves. It's a lot easier to calculate the intersection between lines and planes if our planes are parallel to the X, Y, and Z axes. So at the moment, if we're looking down the y-axis, so let's say this is a plan view looking down, this is our viewing frustum. Okay, so we have we have four sides, so left and right, top and bottom, which aren't parallel to our X, Y, and Z axes. That makes work difficult. What we want, or what we actually do, is we want to transform this viewing region so that it's a unit cube. Okay, so the near viewing plane is this one at the bottom, so that's -1 on the Z-axis or the ZS-axis. The far viewing plane, this one at the top, is then at 1 along the Z-axis, and this right sloping side here is this side here, which is at 1 on the X-axis. Okay, so we're sort of taking a cone shape, we want to transform it so it's then a cube shape. To do that, that's quite simple. Okay, we need a transformation in the horizontal direction. Okay, so we want something that maps our left coordinate to -1 and our right hand coordinate to 1. So we want a mapping. L is simply minus whatever the right coordinate is, because we have, if I go back a couple of slides, our center of our screen is at the origin. So this right coordinate is simply minus whatever the L coordinate is, and vice versa. Okay, so what we have is we need our X coordinate for our screen space to be somewhere in this range, -R to R. What I want to do now is I want to apply some sort of jiggery-pokery to this, so that this number on the left is -1, and this number on the right is 1. So to do that, add R to both sides, or add R to all three parts. Okay, so -R add R is 0, XS add R is XS plus R plus R is 2R. Divide throughout by 2R. Okay, so if we divide the middle bit by 2R, we get XS over 2R plus 1 over 2. And of course, we have our 1 on the right-hand side. So we now got our 1 on the right-hand side. We somehow need to get it so this is -1 on the left. Okay, what have I done here? I've multiplied both sides, all sides by 2. Okay, so multiplied throughout by 2. Subtract 1, and we get that. So this is our mapping. So I've mapped the XS coordinate, so it's between -R to R, and now it's, if I divide XS by R, it's now between -1 and 1. Okay, so that's the that's transforming it. We also need to combine this with perspective projection. So if you remember, perspective projection for the X screen space coordinate is simply n divided by z times x. So instead of XS, I just substitute this in. Okay, this is my mapping. Okay, and you could do the same for the Y direction. Y just in terms of T and B. Pretty much the same thing. Okay, so then if we combine that with the projection matrix, that's what we get. Okay, so these first two elements on the main diagonal is to do with the X and Y coordinate. Okay, so these are the sort of X and Y plane. We have two unknowns here, A and B, to do with the Z. Okay, how far, what's the distance, near and far? Okay, so we've done the sort of left, right, top, bottom one. Now we have to do near and far. Okay, quite simply, if we multiply out for ZS, we get A times Z plus B over Z. Now Z, for the near viewing plane, is equal to N. Okay, that's the distance to the near viewing plane. And for the far viewing plane, the Z coordinate equals F. So what this gives me is simultaneous equations. Okay, so A and B are the solutions, and they're going to be in terms of N and F. Simple algebra, solve these two equations, we get these. Okay, A and B there. So substitute them back in. That's the matrix. This is part of what you're going to have to do for the assignment 7. Okay, you're going to have to calculate what that matrix is for a given viewing frustum and then apply it. Okay, so that's a complete transformation. It combines the perspective projection with the scaling of the viewing frustum. So you should end up with a unit cube. I can show you that a little bit better with the actual ones. Okay, so here I have an aligned world space, and I've superimposed my viewing frustum onto it. So that's my viewing position. I'm looking along the arrow, and this sort of is my screen. So I've put in a particular, I think it's something like 90 degrees or 45 degrees there as a field of view. Okay, so, and I've also inserted a far viewing plane. So that's your viewing frustum. Anything outside this viewing frustum should be clipped. So this edge of this building here needs to be clipped away, the back of that sort of church-like tower thing, and that edge there. So anything outside of these sort of blue lines needs to be clipped. Okay, that's the untransformed aligned world space. Where's the clip space? Bear with me 1 second. Okay, this is the transformed screen space. Okay, so as you can see, this viewing frustum is now a unit cube. Okay, so it goes from -1 to 1, -1 to 1, and also in the Z -1 to 1. So that combines the perspective projection with the scaling of that viewing frustum. Okay. And you can see now we've still got the same bits of the building which need to be clipped. It's a lot easier to clip because to a cube than it is to clip to that sort of slopey edge viewing frustum. Okay, just about finished there. Your assignment 7, in order to complete it, you've got to do what's called the Sutherland-Hodgman algorithm, which we won't cover until lecture 3. But you can do the first question now. Okay, the first question of the assignment is essentially applying this. Okay, applying this matrix to a cube or to a polygon and seeing what the coordinates are. I forgot to send around the sign-in sheet, but you're all here, so I just mark you all down as here. Easy. Are there any questions regarding what we did today? Not all of my sessions will be this passive for you. Normally I get you doing some activities, but today I just wanted to sort of recap. Okay, so I'll see some of you in the lab in a minute.